Zet de deuren maar open en struin naar huiskamer maar.
Hi everybody, I'm Marcus Fayers, founder and editor-in-chief of Dezeen, the online architecture and design magazine, and welcome to this talk, Good Design for a Bad World, Carbon. Good Design for a Bad World is a talk series and concept that we've worked together on with Dutch Design Week for a few years now. The idea is to look at some of the problems the world is facing and see if architecture and design can help solve those problems. I mean, the politicians haven't been able to solve the refugee crisis, for example, or the pollution crisis. And so we did a talk about that a couple of years ago at Dutch Design Week. We were looking at pollution and climate change and things like that. And today's talk is about carbon. How can the COP26 climate conference is coming up? The world is going to get together and try and discuss how to solve the problem of climate change. And of course, fundamental to that is the fact that too much carbon is in the atmosphere rather than on Earth. If we can start to remove that carbon from the atmosphere, we can start to make a difference to climate change. And carbon is actually an amazing material, as we're going to hear from our panelists. Dezeen did an editorial series earlier this summer called Carbon Revolution, where we looked at ways that you can do precisely that, start to take carbon from the atmosphere and use it on Earth. This is one of the things we wrote about. It's a company called Climeworks who build big machines that literally suck carbon out of the atmosphere. And there's other ways of doing it as well, using biomaterials such as mycelium, for example, which grows naturally, absorbs carbon, and then you can use it for all kinds of things. So that's a preamble to the talk. I'm going to introduce you to our amazing panelists. First of all, we have Darshil Shah, who's a materials scientist from Cambridge University. Darshil, tell us a little bit about what you do.
Sure, yeah. So I'm an associate professor in materials at Cambridge. I'm in the architecture department, and there I work alongside in a very multidisciplinary group in the Center for Natural Material Innovation with plant scientists, biologists, chemists, engineers, architects, physicists as well. And together we are trying to understand how we can use plant-based materials as alternatives to high carbon materials or high energy materials in the built environment, but also elsewhere. And we work on across length scales from the fundamentals of how these molecules come together to form things like cellulose, and also then resynthesize them to produce our own inspired materials for real world applications.
And to put it in very, very simple terms, if you build a building using plants or trees, those plants during their life have taken carbon from the atmosphere, and then you can lock them into the building in essential language.
That's correct, yeah. So a plant or a tree is basically a carbon sink, and it will be taking up carbon dioxide and then processing it, releasing the oxygen, and then converting that carbon, primarily putting it into the cell wall materials, mainly in the stalk or the stem of the plant. And then when we harvest or cultivate the plant, we can extract the material which has stored carbon in it and then use it to put it in the fabric of a building in which it's stored for long periods of time.
Hélène Chartier is head of zero carbon development at C40 Cities. That's a very long job title. Hélène, tell us a little bit about what that means and what you do.
Yes, thank you. So first of all, what is C40 Cities? So we are a network of 100 megacities, New York, Paris, London, Sydney, and more, who are working together to really try to accelerate their transition toward a net zero future in cities. And I'm working on all of the built environment and urbanism aspects, so really working with cities to try to develop their policies, their regulation to accelerate this transition, and also try to develop programs and initiatives that can develop landmark projects that use this type of materials or other technology that could really accelerate the transformation of the built environment, which is today one of the main contributors of climate change.
I mean, it's 40%, I think that's the widely given statistic, isn't it? That the built environment, the buildings, the infrastructure that we all live in and use is responsible for about 40% of all global warming
globally, 40%, but if you look only cities, is more than 50, 60%. So in the city itself, that's really the major contributor of emission.
Thank you very much. And finally, Teresa van Dongen. Teresa is a biodesigner who's been working with natural materials for a very long time and has recently been looking into carbon capturing materials. Teresa, tell us a little bit about yourself.
Yeah, thank you. So I'm a designer, and I started out once studying biology, and I ended up combining these two fascinations in my studio. And inside my studio, I think what a big fascination always is to try and incorporate scientific developments and innovations into my works, because I've been noticing that innovation, it takes a long time for it to be implemented. It takes years. And I think designers can look at innovation from a different perspective and work much faster on a smaller scale. And that's actually what I find most interesting about collaborating as a designer with scientists.
Great. Well, each of our speakers is going to give a short presentation to explain better what it is they do, and then we'll end up with a discussion about how much of a difference can architecture and design make to solving climate change by using carbon in a better way.
Fantastic.
Over to you, Darshil.
Thank you. Yes, so we just touched recently on the point that the built environment is responsible for 40% or more of carbon emissions globally, but within that, even materials have a huge impact on carbon emissions, on climate change in general. And in fact, we have reached a tipping point very recently in which anthropogenic mass, so the mass of all human-made materials, generated stuff, has exceeded living biogenic mass, so the mass of all plants and animals. And in fact, if you look at the amount of materials, concrete and aggregates account for over 85% of anthropogenic mass in total. So that's quite a huge amount. Annually, we produce 100 billion meter cubed of material, and over 80% of that tends to be concrete or aggregates or bricks, mineral-based materials. And so there is a real need for us to transition back into more renewable, less energy-intensive materials, as we did pre-industrial revolution effectively. And one of the most abundant bioresources on our planet is cellulose, which is a material that we work with. And cellulose is formed or found, is the main building block of plants, and particularly found in the stems of trees like beech, in hemp stalks as well. And during the process of growth, these plants are acting as carbon capture factories and then storing the carbon very efficiently by giving the oxygen for our benefit. Each kilogram of plant-based material will be holding 1.4 to 1.8 kilograms of carbon dioxide. So quite efficient in that way. But even so, depending on the species of the plant, depending on the rate at which they grow, depending on the densities at which we can grow them as well, some are more efficient than others. So for example, a beech forest would sequester somewhere between 6 to 8 tons of carbon dioxide per hectare, whereas a hemp plant, because it grows so rapidly, in 100 days, effectively, it will sequester of the order of up to 15 tons of carbon dioxide per hectare per annum. So I can talk a bit more about some of these materials. When we harvest these materials, for example, from the hemp crop, we can harvest the stalks, and we get two primary resources. We get chives, which are a woody, barky sort of material, from which, for the built environment, we can produce materials like hempcrete, which is an insulation, non-structural material. But you can also get very high-quality fibers, which have historically been used for paper for thousands and thousands of years, actually, and also for textile applications, producing very intricate fabrics, but also now for automotive applications and for the built environment as well. You can convert the fibers into composites by impregnating these with polymers, which can be petrochemical based, but also increasingly bio-based, from seed oils from hemp, from soybean seed oils, from cashew nut seed oils, for example. So using agricultural and productive landscapes to produce our materials. And within that, the carbon is going to be stored in this sort of material. These components are really strong and stiff, and one of the advantages of their high strength to weight ratios, high stiffness to weight ratios, but also their damping properties, their vibration resistant, means that you can produce quite functional products. They have been used in automotive industry for over 20 years or so now, for instrumental panels inside the cars, but also for tennis rackets, for ski poles, for surfboards, and lots of consumer products. And we are also looking of their uses for compostable materials, for plant pots, as well as for long lifespan applications, for example, in wind turbine blades or in the built environment sector. We cannot forget mass timber, or timber especially. That is one of the most abundant biomaterials, and given the scale of the challenge, this is going to be the material that we need to be working with more as architects, as designers over the next 10, 15 years particularly, while we crunch down on the climate challenge problem. This was a pavilion that our group put together for the London Design Biennale recently, which is designed origami folded from a flat 2D sheet of plywood, actually, and then it's folded into this beautiful form using a kerfing technique, so in which you're making precise incision cuts. And that, again, shows partly the innovation that is possible and increasingly happening with materials like timber, in which you can also make transparent timber, you can make radiative cooling timber, you can make compressed and densified timbers that are stronger than steel. So lots of different innovations. You can weld timber without any glues in a matter of seconds as well. That's something we're working on. But in this case, we are also demonstrating how you can create flexible forms with natural materials that are fabricated using digital design methods, which are increasingly becoming important, as well as that are deconstructible. And I think an important element of using biomaterials, and that's the direction we are headed in, is circularity and making sure that the carbon is stored within them for as long as possible so that they are deconstructible, disassemblable, and then you can reuse them, or then thinking about cascading flows. One of the figures I always remember is that 50% of annual wood resources end up as fuel, so they're just burned, rather than being used for more long-term applications, which are going to be storing the carbon. Bamboo is another fantastic resource that we have. Less than 1% of global plants species are bamboo, but you can get lots of material from it because it is really fast-growing. So it grows a millimeter every 90 seconds, and it matures every 3 to 5 years. And it means also you can get multiple harvests over its life, 30-year life, for example. And in this case, this was a pavilion actually we showcased in Amsterdam, which, again, using digital parametric design, we were showcasing heat bending of bamboo, deconstructible, again, using bamboo connections, and self-supporting as well. Showcasing some of the innovations that can be done with the whole culm form of the material, but also you can laminate the material to generate a wide variety of forms. Now, biogenic materials are going to be important, but because we have a reliance on mineral-based materials, we cannot forget the importance that earth-based materials will also have. And in this case, this is a stadium, a cricket stadium in Rwanda that Michael Ramage, Anna Gatto from our group, who are also partners at Lighter Designs, they put together using compressed earth, unfired, and locally available resources using geogrid textiles to build this beautiful form. So again, it's trying to show innovations that's possible at scale, using local low-value skills and techniques to produce beautiful structures using low-energy materials. And that is what we increasingly need to be doing.
Great. And you showed us, you held up these materials. Can you tell us exactly what these are?
Sure, yeah. So this, for example, is a hemp bioresin-based composite material. It's actually for rain screens. It's produced by Marjan Farms, in which a non-woven fabric using needle punching techniques is impregnated with a sugar-based resin. It's derived from waste bagasse. And it's completely hemicellulose derived, so it has interesting fire properties as well. So some of the applications are also in galley carts in aircrafts. One of the challenges with this sort of material for architectural applications would be how its properties, particularly its color, for example, might evolve over time as well. So some long-term tests are something we're looking at, but also, again, thinking about circularity. So because it's a thermoset-based material, it is non-compostable, it is recyclable, it is downcyclable, but not recyclable. And I think the vocabulary and the terminologies we use is something we need to get more familiar and upfront about as well. So this is not completely sustainable, because apart from carbon, we have the waste problem, and building more plastics in our soils is something we need to be moving away from. But it's a start away from petrochemical-based resins and petrochemical-based fibers, or at least high-energy fibers. And then a non-structural application is using these textiles, which you can there's a lot of industry. We've been making textiles for thousands of years. We've recently looked at how the Egyptians made linen fiber and their beautiful textiles 4,000 years ago, and our techniques haven't changed that much, interestingly. Some things have evolved, but apart from that, the most types of fabrics have remained the same, and in this case, it's impregnated with a compostable PLA-based matrix in an industrial compost facility, replacing carbon epoxy for some of these camera casings. So again, some consumer goods that you can produce that are non-structural, but also structural from these sorts of fabrics. And
you mentioned wind turbine blades. Because we were talking about this before, and you were saying that wind turbines, of course, great, they produce renewable energy, but at the end of their life, you have a big waste problem. So tell us about your work with wind turbines.
Yeah, so that is the elephant in the room in the wind energy sector, actually, because the carbon payback period of a wind turbine is about 9 months to 12 months, depending on the size of the turbine. But the towers, although they can be made from recyclable steel, they are quite heavy, and they require significant amount of concrete for their foundations, particularly also if they're offshore, so taking that amount of material out there. And in fact, even the tower and the foundations account for about 40 to 50% of the carbon emissions of a wind turbine up front. And then it will recover that, obviously, over its time. But the blades, which are made from fiberglass or carbon fiber composites or a hybrid of these, are not recyclable. They are not incineratable, because both carbon and glass are resistant to high temperatures, so you cannot burn them for energy recovery. So they are landfilled on large scales in the US and developed countries, which is quite scary. And we need to rapidly be thinking about, again, design for disassembly or deconstruction on these applications. And I think apart from the collaboration between designers, engineers, architects, material scientists, and biologists that is needed, something that we need to get more active about is learning from the mistakes and the improvements in different sectors. And I think that's one of the big credits that designers can do, because they're not often bound to a particular application. They have a much wider view.
And you will need a big landfill site to bury a wind turbine blade because they're, what, I don't know, 20, 30 meters long? They're really
yeah, much longer actually. So now, 5 years ago, the largest wind turbines were 8 megawatts, but now they are producing 16 megawatt wind turbines, which will have wind turbine blades of 120 to 150 meters. So that's much larger than a span of the whole airplane wing.
And could you potentially make those wind turbine blades from hemp?
So that's something we are looking at more particularly. We might have to hybridize these because of the amount of stresses and strains they face. There's also looking at how to use thermoplastic-based matrices that are possibly recyclable rather than thermosets, which are not. But we are, at least for small wind turbine blades, I think that's the start, because there has not been even advancements in that sectors for 3-meter or 5-meter wind turbine blades that could power 5 to 15 homes or farms, for example. Even those using these sorts of linen or hemp or cotton or jute or sisal, depending on the regions you come across from the world, because you might grow sisal in Kenya and in Brazil or Peru, but you may grow linen in France and in Germany and Romania. So you can use a variety of these plant fibers for these sorts of applications because the properties are not very dissimilar.
Great, thank you so much. Over to you now, Hélène. Tell us how cities are trying to build zero carbon developments.
Yeah, so I mean, cities are doing quite a lot of different things, but on the built environment, they really try as well to accelerate their regulation. So we just maybe, yeah. So I really would like to give a little bit of example of cities and the stakeholders are working together to decarbonize the built environment. Again, we mentioned 50% of the emission of cities. A new city the size of New York is built every month in the world. So as well, there is a question about the trend of the construction, and we know that today 70% of 55% of the population is living in cities, and it should grow to 70% by 2050. So really the way we plan, we build, we design our city are going to make a huge difference. We know what we speak about, what do we mean about emission in building. There is really two categories of emission, what we call the operational emission, which really it's calculated annually, and it's really the emission that is used while the building are in operation. And for these emission, we know that what the hierarchy of priority is really to start by reducing the energy that is used in buildings, so the way we design the retrofit of the building, which is a big challenge. Today, only 1% of the building are retrofitted every year, so we definitely need to accelerate quickly the retrofit of building. And in terms of target, every new building must be net zero emission today in operation, which is something that we know how to do, so it's totally possible. And we need, as I mentioned, to accelerate the retrofit of existing building. There is another category of emission, that the one you speak about, which has been totally neglected in the past. So it's really a new emission that has been taken in consideration, I would say, since a few years now, really. And it's really about the emission that is produced from the construction itself. So before the building is in use and at the end of the life. So what we call the embodied emission. And this is approximately 1/3 of the emission. Operational is 2/3. But the question is that it comes up front. It's come at the beginning of the life. So it's a very strong lever to accelerate quickly the reduction of cities' emission. So really there is a lot of work in this domain right now. We know that cement and steel are especially very quite terrible in terms of their emissions. That's why there is a lot of research and everything. In terms of what we must do to reduce embodied emission, the first thing is start, and I mentioned the rate of construction is also to start to reduce a little bit the construction, so making the most of the existing asset, making the most of the existing building. and extend the lifespan of the building to avoid, to accelerate this cycle, demolition, reconstruction. We know, for example, in a city like Paris, a building is used only 40% of the time. So that means 60% of the time is empty. So there is something about how we design a place to we maximize the use, we optimize the use of its thing. The second thing is really to design efficiently. So there is a lot of way to reduce the amount of material we use. It's not just about the material itself, it's about reducing the use. So for example, and I'm going to give several examples, the basement, the underground is really much more embodied emission intensive than the hyperstructure. So each time we add a parking level, for example, it's in terms of concrete, use of concrete, it's a catastrophe. So there is a lot of things to think about how we could design more efficiently our building. Then really about using lower carbon emission materials, and you gave a great example. And also there is something about the transport of these material, because embodied is really about extracting, transporting, assembling all of these material. So also use low carbon engines, so electrification of all of the engine, which is as well very interesting for pollution and other. So in terms of targets, so really what we must do now is really make mandatory life cycle assessment. We need to calculate this embodied emission, because for years all of the carbon life cycle assessment was the carbon assessment was totally not considering all of this embodied carbon, and we need to reduce today 50% of the embodied carbon that the target. We know it's approximately impossible to do zero carbon embodied, but at least reduce 50%. It would be already a good target. Just as well, I just wanted very quickly to mention, because as a designer, I think they don't just build box, but they really build a place where people live. I mentioned the use of rate of the building and everything, but also the way they design can really empower people to live a more sustainable life, and we know that the consumption-based emissions are very, as well, something that has been not taken in consideration enough when they do the carbon. When a city or a nation say, I will be carbon neutral, they totally avoid thinking about all of the consumption of the people, which is a very large problem as well. So design to empower people to make lower choice as well in their daily life. Just wanted to give a few examples. We have at C40, we have run a competition called Reinventing City to try to push city and to work with stakeholders to develop landmark projects who could really inspire for a zero carbon future. We have been working with that with 14 cities, 32 projects, and I just wanted to give a few examples of this project, and you allow me to take my note there. So this project, for example, Living Landscape in Reykjavik, it's the designer, the architect, it's Jacob and McFarlane. And this building will be the largest wooden building in Iceland. And this is a very interesting building because, again, to reduce embodied, they remove all of the parking, all of the basements. They also target zero emission in zero carbon in a lifespan. So not only the embodied, but also the operation. So that's also very interesting, and they totally develop a pioneer project in Iceland in terms of electrification of the construction site, the construction engine. So that's a very interesting project. Another one in Milan, recently announced, the lead architect is Noeta with Barreca Lavara and Zino Zucchi, and this project convert industrial site in Milan for 14 hectares to the first carbon negative project in the city. So in operation, I would say, thanks to really they develop a district energy system that will not only power the new neighborhood, but also the nearby neighborhood. And in terms of embodied carbon, they target 52% of reduction, thanks to reuse of the existing material, use of wood construction as well, and also 1/3 of the material that will be used on the site will be recycling material. So 1/3 of the construction material will come from recycling material. So quite a lot of solution. Another project in Montreal, a little bit similar as well, a former industrial site that will be totally repurposed, reused for artistic and entrepreneurial hub. And also very interesting, 84% of embodied emissions. So that's probably one of the most, at least that I know, that in terms of emission reduction, again, it's very interesting to see that it's not one strategy. It's very a wide range of strategies that could allow this type of target. So no basement, no parking. All of the new construction are in wood, in structure, in the wall, in the floor, and reuse of the existing, not only the building, but also the materials that is available on site. It's also net zero on operation and a lot of other very interesting projects. This project is interesting in Chicago, the first net zero building of high-rise of Chicago. It's interesting because not only they reach to net zero operational through on-site supply of renewable energy, but also in Chicago they don't allow wooden construction because they have been a little bit traumatized with the fire. So it's not allowed to build in wood. So it was a big challenge for as well the team. So this project is led by Studio Gang, Ginny Gang, and her team. And they developed a project where they, again, remove all of the basements, all of the parking, which is quite rare for a high building in Chicago. And they work with a local cement factory who try really to reduce so there is a lot of techniques that they try also to reduce the carbon emission of cement, and she really also try to design to use the minimum of amount of materials. It's also a very interesting project because it's really combining social aspect. It's 100% social housing, and all of the basement, it's really for minority community of Chicago and others. So very interesting project. This one, the Collective for Climate in Paris, in La Porte de Montreuil, so quite large project as well. It's the first neighborhood, zero carbon neighborhood of Paris, and in a lifespan, so embodied and operational. And I think they have really tried to push as well the question of the materials in Paris. So 100 structure in wood and a bit of stone, local stone, that all come from France, because the question of where the material come from is very important. All of the facade and is made of hemp as well, hemp or mud brick that come from the Greater Paris area. So the question of where the material come from is also very important, and other type of solution. This one in Oslo, Recipe for Future Living, is interesting because it's really about reducing 90% of the embodied emission by really pushing the use of recycling materials. So they basically create a form of fair with demolition site to try to see if they could reuse a maximum for every type of structure and walls and everything. So it's very, very interesting. This one in Singapore, it's really about reusing an existing site and retrofit all of to reach net zero emission. And of course, because you don't build again, you limit the amount. And this one is interesting. It's a very different project in Madrid for logistic hub that will be powered by hydrogen. And it's also very interesting because it's all about using wood, but also prefabricate. So it can be disassembled entirely at the end of its life, and many others. So I just try to give an idea of the different strategy that the designer try to develop to reduce the emission of their project.
And all of these projects that you've shown, they're going to get built, are they? And they're going to act as test cases for how far you can...
All of these projects are now in phase of implementation. So some have started their construction, some are about to start, and they are on their way now.
You mentioned that one of them will be carbon negative in operation. So what does that mean exactly, and how do they achieve that?
So basically, it means that they will produce more they will design in a passive way and everything, but then they will produce on site more renewable energy that they need, actually. So they will supply the nearby neighborhood, for example, which is basically a great way to have a form of local offset, so they can help building other neighborhoods to reduce their own carbon footprint. So that's I think, a very interesting way.
And you said that legislation is needed in order to kind of almost force people to think about embodied carbon. Is that going to happen? I mean, the kind of construction industry is very strong connections with government, especially in my country. Do you think we'll see those kind of changes in the law around the world?
I think we see that, I think, pretty much in operational emission. So a lot of cities are taking the regulation and everything. Embodied is really a new topic. So we see there is a lot of a lot of sectors that need to be structured. So the cities are a little bit, to take a regulation without the sector being ready. So they are a little bit shy, I would say, to start. But the first thing they need is first to push the sector to disclose their emission, their embodied, to know how to analyze, to evaluate. And then in a couple of years to try to put the first regulation on reduction. So that's, I think, except a few cities like Oslo, Vancouver, who try to force off reduction emission in embodied, it's starting, but it's really new. It's really new. Yeah.
Great. Thank you very much. If you could pass the clicker now to Teresa.
Yeah. So I think just some background. I'm usually more known for my work with microbes. And in this installation, it's working with, it's a light installation actually working on bioluminescent bacteria. It's one luminous dot, it's from 2015. And I'm just going to quickly skip through it as a background. This is Electric Life. It's something different. It's also working on microbes, but these are electroactive microbes, so they produce energy for artificial light. And what I actually want to tell in this topic is that over the past years that I've been working on these projects, usually in the scientific centers that I visit to work on them, to develop them, I was coming across a lot of initiatives working with greenhouse gases and showing me that actually greenhouse gases are very valuable. And just to start with one example, in 2016, I saw a very similar scientific setup as this one. And what was happening here is that actually so there are microbes which are capturing methane gas, which is a much stronger greenhouse gas actually than CO2. They're taking it in and they're producing proteins from it. And as you may know, methane gas, it's usually released by the cattle industry, so through burps and farts, etc. But these proteins, again, they are possibly food or feed, again, for the cattle. So this was an actually beautiful circular example that I saw of how you can start to use greenhouse gases for a purpose. So I started to collect, for instance, starting with these proteins, a material library or food library, mainly materials, because I thought a lot of people don't know about this, and it would be interesting to have a little bit of an overview what I've been coming across. And fantasizing also with these proteins of how humans maybe in the future could eat microbial proteins. That would also solve a lot of problems that we have with food, because you need a lot less land for microbes producing food instead of agriculture. So on the more technical side, I also started to work with institutes like VITO, which is a Belgian institute. It's the Flemish Institute for Technological Research. And what they're doing is also really interesting, also what you mentioned, how the steel industry has such a big footprint. They are, for instance, using waste streams like steel slags. The steel slags are usually quite an element which is quite polluted in a way, so they are purifying these waste streams and then creating a formula with them which you can make, for instance, a concrete. But this formula, it can take up about its own no, let me put it differently. The amount of CO2 that concrete would usually emit, that amount, this type of concrete can actually take in CO2. And that, in their process, it happens in this high-pressure CO2 chambers, where they harden out their formula into a concrete with CO2. So this is really a revolutionary change in the field of building materials, actually. But a lot of their materials, instead of the one that I just showed, it's Carbinox, that one actually has had implementation trial in Ghent, so they made a first piece of pavement with it. But a lot of their materials that they're developing, like also 3D printed versions or other ones with other colors using different formula, also actually they're using waste streams from the demolition waste or concrete waste, which is the second largest waste stream in Europe, which is quite logic, realizing how much it's used. So they're using all these kind of waste materials to create types of concrete that take in CO2. So this is more kind of the technical materials that I have now in this library, but there's also more natural ones that I want to mention briefly. With what you're seeing here, it's called olivine. It's a mineral, and you can usually find it in volcanic areas. And what's special about this mineral is it can take almost about its own body mass. It can take in that amount of CO2 when it's grinded to a form of sand. And the special thing about this sand, the moment that it has been carbonized, when it has sequestered the carbon, it has a kind of a calcareous property. And what does that mean? That means that you can actually use it as a replacement for binders in products like PLA printing filament or paper, or also in cement, concrete-like materials. You can use this olivine as a binder. So this paper, for instance, it's now being produced by Green Minerals. It's the first 1,000 kilograms is going to be produced this year using this mineral olivine. So these are just a few examples of the materials that I've been collecting. And they're all kind of materials of which I think they're not very well known. They usually still live in laboratory or science centers. The process for them to be implemented is probably going to be still a long one. But can we look at them from a different perspective, from maybe bottom up? Or so I've put them in a physical and an online material library that you can visit it online, and each and every material will give a description. So it's stuck a little, but for instance, the Carbinox that I was telling you about, you can find that it takes in 200 kilograms of CO2, whereas usually, the video is a bit bumpy, whereas usually it would emit 200 kilograms of CO2 per cubic meter. And you can see the physical library at the exhibition. It's in our nature. And what I think I'm trying to tell actually with this library is that we've come to see carbon dioxide and other greenhouse gases in quite a negative daylight, for obvious reasons, of course. But yeah, I mean, we still live in a capitalist society, but if you look at materials like this, you can also imagine that they really have that this carbon dioxide and greenhouse gases, they have value. And something of value, why would we ventilate that into our atmosphere? If you were imagining that we were ventilating gold into our atmosphere, we would not do that. We would go for it. And what I'm trying to say is actually, I think carbon dioxide and other greenhouse gases, they are gold. They're worth something. So let's go for it.
Thank you very much. And if you could just click on to the next holding slide. So since you set up this materials library, what's happened? Have people been getting in touch with you? Have you been sort of having to send samples to people? How is it growing?
Yeah. So getting all kinds of different responses and reactions from a scientific perspective, but also mainly actually, for instance, other material libraries who would like to just include the whole library in their material library, or people who want to do a project with one or two of the materials. And up till now, I've mainly been collecting and keeping in touch with these people and collecting their requests to see where this could go. Because the difficult thing about these materials is usually that they have a kind of a life in the lab still. So what is the question I'm finally going to ask them? Usually they are willing to create maybe a 1 of 2 of 3 of, but they are not producers, you know. So I hope that also this will just start to change the way that we are working together with science institutes, and that they would become more open also to work together with unexpected parties. And you see that some of them are already doing that. So like with the olivine, it starts as a natural mineral, but actually the carbonization can become quite technical if you want it to be fast. Then you also need to bombard it actually with CO2 in a pressure chamber. So, and this initiative is actually very open to collaborations, and that is a process that I'm interested to see where it's gonna take us. Yeah.
So it's interesting. So Darshil was talking largely about materials that absorb carbon whilst they're growing, and then you stick them in a building. And you're talking about materials that then capture carbon dioxide in their use. So there's this like two different sides of the coin. But actually, a question for both of you: how do we get these materials out of the laboratory or out of the little sample and to being used? How can we, and Hélène, if you have a point on this as well, how do we get people to start trying these things out? Because people tend to be quite conservative, don't they? Especially if there's a lot of money at stake. So they'll stick with concrete or they'll stick with plastic because they know it works and they know how much it's going to cost.
Do you want to go first?
It's a very good and very it's a difficult question. I mean, from my perspective, I think it would be interesting to not only look at these materials from a large-scale implementation, so because they also have a bigger chance to fail because of maybe not being profitable enough, but to try and see if these kinds of libraries or the exhibitions and the talks, we can get them to also work together with us and not only wait to patent it and sell it to a big company, but to see if they can be up for the smaller initiatives and grow from there. But this is something that is not happening so much yet. So that would be quite new to approach it from that perspective.
Yeah, if I can add to that, I think it's also probably early collaboration and discussions with designers and scientists, for example, because sometimes they are working at different scales. They may be also working on different properties, because an engineer might be thinking about increasing the strength by 10%, whereas a designer might also be thinking about some of the social properties of the material or some of how the color, for example, or the texture might evolve. And I think the other aspect of that to add is the processing. And I think education from both sides of how it is, how materials are formed into shape, because I think that's a big part of design, giving it form. And I think that is through processing and manufacture, and an understanding from both points of views of how that is done is quite important for that to actually take place. Exactly.
And Hélène, the cities that you're working with, do they find it easy to get permission to use some of these more innovative biomaterials? Because often, you were talking before about timber, there's an assumption that a wooden building will burn easily, which actually isn't true, but there's a legislation, there's a law in place to stop that. So how do these developments you were talking about, how do they get permission to do more experimental things?
So I think there is two steps here. I think there is a step of allowing a specific experimentation, like a competition like the one I just showed, and then it's a step to see how it works, and then it goes to legislation. So I think, of course, it's the city need to make sure, we didn't mention, but the question of preparing the sector is very important, because it's not just about fire legislation, it's about the cost of construction. All of these main cities we are speaking of, they are facing as well housing crises, with a very important question about the cost of the housing. So if the cost of construction go very quickly up, they can face as well big social problem. So it's really about, that's where there is a little bit of doubt of accelerating this type of action. But I think, as you have said, I think it's very important to try things, but also to mainstream. So for example, wood construction, the question of parking regulation to really quickly reduce the question of reversibility of the space, to try to, we know a lot of buildings are basically demolished because we can't change their use, and so the question of designing reversible building and everything. So there is things who can be quickly mainstream, and then we need to have research and to push for the tomorrow's material. So I think what is important is to give space for both, to mainstream quickly, put as well the question of measurement at the heart of the design. So every decision, and now we have digital tools that help designer, developer to really think about this question while they are doing, make sure they disclose their strategy and their target, and then and mainstream what is already ready to be mainstream, and at the same time push for experimentation, collaboration with people like you guys to try to and tomorrow make sure that this can become mainstream. But I think there is few things that are not ready to be mainstream, but there is things that are. So we should,
I love that idea of putting measurement at the heart of design, and I think what goes with that is making sure that you're calculating the embodied energy and the life cycle carbon, but also moving away from prescriptive building standards or design guides and more to performance-based design, in which if you can demonstrate that the building is safe, then you should be able to build with those materials. And I think it's well established now. We have quite a few buildings that have used mass timber for decades now, and I think they perform really well, and they are good at storing the carbon, as well as reducing on-site construction times, for example, congestion as well, because we are living in increasingly urbanized areas. So reducing truck deliveries of concrete will significantly improve traffic related to that. And also, I think related to that is thinking about how the economies and the contracting of the built environment is done, particularly because cost is often brought up as a factor with some of these newer materials like timber, but then the higher costs may be related to the material, but you may save costs on construction times or in maintenance. So I think having a whole life cycle cost analysis and understanding would go a good way in making sure that these materials become more mainstream as well.
And Hélène, you made a good point about consumption-based emissions. So you could build the greenest housing block in the world, but if everyone who lives in that block is eating steak that's been flown in from Argentina and drinking mineral water from bottles and turning their heating up, is kind of pointless, and driving a big SUV around all day. No,
I think it's again, I mentioned it quickly, but I think today when the city, a nation say they are going to be carbon neutral in 2030, in 2050, they don't consider everything. They basically consider the emission produced in their territory. But the scope 3, the famous scope 3, which include embodied carbon from construction and basically the embodied carbon for any good, you think most of these emissions are produced outside the territory. And if you just don't look at these, it's a catastrophe. So if we take the city of Copenhagen, one of the most ambitious cities in terms of carbon neutrality objective and everything, if you add the consumption-based emission, today they are just going worse and worse. So that means we need to include all of the thinking about the supply chain of our goods, which are not produced within our territory, which are produced outside, but it's a change of mindset. And that's very, very, very important.
And sorry, you were going to say something, Teresa?
I was going to ask, how does it work then with do you think about in the housing, for instance, that if you have more communal space instead of big private space with everything doubled, you know, like everybody has their own washing machine. If you have more communal space where you share that also saves a lot of carbon.
That's an excellent, I think, for example, when I say reducing the construction, it's also something about individual house. I think today we can't afford anymore developing individual house. That's mean, you know, all of the thinking we need to reduce maybe the personal space because, but also that means creating innovative way to share space, to share some equipment. Do we need all of the equipment we have? If there is a place where you can, close to where you live, where there is all of the basic equipment you don't need individually because you use it 5 times a year. So there is a lot of thinking there, I think, and the designer could be, the architect and everything could be really very, you know,
that's great.
Pioneer on that.
And Teresa, you were talking about microbial protein, which is a kind of scientific-sounding name for basically food that's made out of greenhouse gases, right? So you could also farm the sky to feed people.
Absolutely, yeah, I think so. And I think most functional is to have this direct capture of the gases which are ventilated from the industry, and to directly capture them and use them for all these kinds of purposes, where you can feed microbes or feed materials with it. And I mean, of course, we probably will have to start storing also carbon dioxide underground, because that's the big idea right now. But before we focus completely on just putting it away, I think it's also very interesting to look at the value of it and what can we do with it, rather than only put it away. Yeah.
And with your material library, how do you know, how can you be convinced that the material does do the carbon capture that it says it does? Because there's a lot of greenwashing going on, there's a lot of carbon washing going on, there's a lot of people saying, oh, I've invented a carbon negative this, and then you look into the science and it doesn't really stack up. So how do you, what's your checking process?
Well, I've been working mainly together with scientific institutes. So they have very strict regulations over publicizing any kind of data. So it's very research based. But it's an interesting point, because there are some initiatives, definitely, mainly I think more from the commercial side, where they are already looking for implementation, which are less scientifically based. They are already taking a little life of their own. And then you have to actually maybe involve scientists to double check it in the end. But most of the materials on the website are still very much scientifically based still, and not out there. Yeah.
Yeah, I think if I can add to that, I think you were talking about whole life carbon calculations for buildings. I think having that done by third parties rather than the designer or the architect or the engineer themselves, I think that's an important way to make sure that these are done based on specific guidelines. I think there's also quite a lot of complex terminology associated with it. What does net zero mean? What does zero carbon mean? And sometimes it is with offset, sometimes it is not. For example, with a reduction of carbon emissions that the concrete industry has made a roadmap of, a lot of it is based on using renewable energy. So they are just changing their energy source. But that could also be done with quite other industries as well. So I think, again, making sure that whether it is cradle to gate or if it is a whole life carbon emission, you're analyzing like for like. That's quite important. And I think people in the world of life cycle assessment know how tricky and difficult that can be to define the boundaries of the assessment and communicating that.
Finally, we have just 2 minutes left. Darshil and Hélène, both of you are going to the COP26 climate conference in Glasgow next month. Briefly, tell us, what are we looking out for there? What could it mean for architects and designers? What changes are you hoping will happen that will affect what designers do?
Yeah, I'm hoping for a lot of action rather than words, as will most of us be. I think some of this related to what Hélène has been talking about as well in terms of reducing the amount of materials. So reduction in materials is quite important, retrofitting, and basically concrete is not a bad material. We have a lot of it around. We should not demolish buildings that are made from concrete and rather change the use of the space and probably retrofit with more renewable or biogenic materials, because there can also be bad retrofits. And again, the whole making sure that measurement of whole life carbon emissions is done accurately and properly. I think having that in the criteria. I think there is also scope of discussing more thinking behind the trade of bio-based materials, because not all regions may have specific resources, and how this would be done, building supply chains along that, and also possibly some dialogue around carbon crediting and budgeting associated with some of these biogenic materials, because currently you do not get, people are talking about afforestation and acquiring carbon credits through that, but I think there should equally be something related to that for storing carbon in timber in buildings and using our cities as carbon sinks. I think if we can get into that sort of thinking and legislating for that, that's what I'm hoping from COP26.
And same question to you, Hélène, briefly.
I think, on my perspective, I think what we need now is that each element of the society, the individual, the business, the cities, the nation, had to put the emission assessment, emission evaluation at the heart of each of their decisions. You were mentioning yesterday that you think about the carbon footprint of your website. Every corporate need to think about what is the emission of my business, what the emission of my life, and I think that's exactly what we need. It's true for building, it's true for everything. And I was mentioning the example of the city of Oslo. I think it's a very interesting example to develop what they call a climate budget. And it's basically they ask to the financial department of the city to calculate the impact, the emission impact of every decision they make. I think it's really what we need. The other thing is about adaptation, because I think we need now and to face that the reality is coming, and there is so much to do on adaptation. And I think there was a fantastic article in The Guardian a few days ago about, it's time to show what's going to happen and to be ready and to change our cities, to change a lot of things just to avoid the catastrophe.
Okay, a slightly alarming note to end on, but thank you so much, Darshil, Hélène, and Teresa, and for our live audience and our online audience as well. Thank you very much.
Thank you.